video, we're going to do an overview of the Mack method and also the Probabilistic Trend Family modeling framework. If you want to get a more detailed understanding of the extended link ratio family modeling framework and also the PTF modeling framework, then I would advise you to study some of our online demonstration videos that you'll find here. You can always pause the video and you'll find them on our website. You can always, once you're on our website, the homepage, you can go to Products, Icofus Plus, and then Demonstration Videos. Demonstration Video 1.2 looks at link ratio techniques that you're all familiar with. Extensions of link ratio techniques, that's called the extended link ratio family. In the first instance, in the extended link ratio family, you formulate link ratios, average link ratios as regression estimators. And the Mack method, in fact, is a link ratio technique, but formulated as a regression estimator. It is equivalent to the volume-weighted averages. Volume-weighted averages are, in fact, average trends, and you can estimate the average trend by using a regression, and that regression is called the Mack method. Murphy is an extension of Mack, where you also add an intercept. For the PTF modeling framework, it might be worthwhile studying demonstration video 1.3, and then if you want to look at applications of the PTF and the extended link ratio family modeling frameworks, there's a lot of studies in Chapter 2. What is the extended link ratio family modeling framework? It starts off with your link ratios, average link ratios. It's extended to include an intercept and also constant trend down each development year in the incrementals. Okay, so let's go to what I call the Mack data. Let's open that. We've got incurred data, ILC, and if we apply link ratio techniques to that, you click on the link ratio technique tab here, and you get a large window. Within Windows, you've got the All tab active, normalized data, ratios. If you scroll down, you've got different selections and so on. And graphs of selections, you can go to the ratio selections tab, where you only have the ratios and the selections. Let's go to selections. The standard chain ladder selection is just volume-weighted averages. It's just a European term for volume-weighted averages, arithmetic average, and so on. By default, the final selection, you can see it's color-coded, is in red. Well, that's by default. If you want to select the arithmetic average, you double-click on the arithmetic average. If you want to select the maximum ratio, you double-click, then that drops out, back to arithmetic average. If you want to select a particular number in a particular cell, you double-click on that, and so on. You can select from your ratios table, you can select from graphs, you can store, and all this is really discussed in the link ratio techniques demonstration video 1.2, and we go to great length to show you all the features and all the flexibility and also report writing and all those kind of things. And then there's lots of examples, and there's also an example to do with report writing right at the end. Okay, there's reports, number 5, reports based on the link ratio techniques module. All right. Now, when you calculate ratios, you are in fact calculating trends or slopes of lines, same thing. And let me just get the highlighter here with the right color. So if you have two development years that are contiguous, adjoining, and you've got Y values here and X values there, this is a cumulative array. Could be paid losses, incurred data, counts, whatever you like. And you graph these Y values versus the X values. And let's suppose now that this is Y1 and this is X1, and this distance is Y1, and that distance is X1. Well, the slope of that line, the ratio Y1 and X1, is the slope of this line. So every ratio is the slope of the line from the number pair to the origin. It's very important, to the origin. The average slope is an average ratio. Every ratio is a slope or a trend. The average slope is like an average ratio. So if you look at the Mack method, there's actually a model behind it, a regression model. You're assuming that given x, the average value of y, the cumulative at the next period, lies on the hypothetical average ratio line or average trend line, same thing. However, given x, the variance of y around the line is proportional to x. Let's make delta equal to 1. So two assumptions. Let's review the two assumptions that is made by the model, and you've got to test that those two assumptions actually apply to the data when you model some data. The first assumption, given this value of x, that's the average value of y. Given this value of x, that's the average value of y. It lies on the hypothetical average ratio line or average trend line. However, given this value of x, the variance of y around the line is proportional to x. So as it gets larger, there's more variance. If you then use weighted least squares, where the weight is the inverse of the variance, so the weight is proportional to 1 on x, you get the volume weighted average as the best line. The best trend line, the best ratio line, the best weighted average ratio line. However, if you set delta equal to 2, then you get the arithmetic average. So let's do it that way now. Excuse me. So if I go to the extended link ratio family, by default, I've estimated the Mack link ratios, which is the volume-weighted averages. And let's see that they are, in fact, the volume-weighted averages. So let's do a comparison. And you can see that the column in these numbers is the same as this row. If I want to calculate the arithmetic average, I then set delta equal to 2. And now I will calculate the arithmetic. So it's a different weighted line, okay, which is the second row. So we don't need that anymore. Let's not use any variance assumption. Otherwise, we'll assume that the variance is constant. So we're just filling a line using ordinary least squares. The weights are all equal to 1. And let's look at the graph of the data. And let's look at the actual data. See if we can interpret the graph of the data. Well, let's see. That's the cumulative at development year 1 on the right versus the cumulative at development year 0. So it's these numbers versus these numbers. Let's select 1984. 1984 has got two numbers. The x value is 5655. The y value is 1155. Then it's this point here. The vertical is about 11,555, and horizontal is 5,000. So the slope of this line, the line between this number pair and the origin, will be the ratio. What is it? So let's go to a table of ratios, and you'll see that for 1984, the ratio is 2.04. That's the 5655 into the 11. If you look at 1985, that's that point here. It's got a huge y value compared to its x value, which is pretty small, and the ratio now is, for 1985, it is 8.759. That's a huge ratio. Now, when you fit this line, which we just have, let's fit it, just that line, just one line. We're only looking at the line between development years 0 and 1. So we've graphed cumulative 0 to 1. That's the line we've just estimated. And the line, the slope of the line, is 2.21724. Okay, so that's the slope of the line, 2.12. Let's call it 2.22. 2.22. Okay, approximation. Now, what about the residuals? You'll see that this is the smallest residual in absolute value. It's negative. That was the 1984 year. So for 1984, this was the 1984 year, right? That's the residual Z, small and negative. You can see, we can get rid of the ratios. You can see that for 1984, the residual is small and negative. That's the residual. It's a standardized residual. You divide by the standard deviation of all the residuals. Okay, so it's small and negative. However, for 1985, the residual, the distance of the point from the line, is huge. Well, you can see it's got a high residual. Okay. So now let's do the same thing from development year 1 to 2. 2 versus 1. So now, let's do the regression 2 versus 1. So now we're doing the next regression. So now we're fitting this red line and calculating the residuals. And you can see that this would be a huge residual there, right? From the red line, there's a huge one there. Which point is it? It's accident year 1987. 1987. That one there, it's got a 10,000. Okay, what's it? 10,000, it's about 11,000. It is that one there. Okay, so now we do all the regressions, or we calculate all the average ratios. So let's do that. And let's calculate the Mack ratios where delta equals 1. And that's all the residuals in all the directions. So that's the residuals versus development year. These are the residuals versus accident year. These are the residuals versus calendar year. And these are the residuals versus fitted values. So if you want to see where this point is in the other graphs, because on the vertical axis it's the same values, this applies to accident year 82, development year 1, the calendar year is 83. Well, it's the sum of the two periods, development period and calendar period. You notice the residuals versus fitted values trend downwards. Remember that residuals represent the trend in the data minus the trend estimated, or the trends estimated by the method. Well, over here it seems like the method overestimates or overfits the big values and underfits the small values. Why? You can see that if you fit a line through the origin, you are overfitting the big and underfitting the small, because a much better line is one with an intercept. That would be called the Murphy method. If you go to the next pair of development periods, you'll see you need an intercept. So it seems like you need an intercept. But if you continue to study on our website, you continue on demo 1.2, we also explain, and I'm going to explain this very briefly, that ratios have no predictive power for this particular data set. And the reason for that is because the incrementals in any one period are not correlated to the previous cumulatives. You know, when you project the cumulatives in the next period, you take the previous cumulatives and multiply by the ratio. But to project the next set of incrementals, you multiply by the ratio minus 1. But you can see that the incrementals in development year 1 are not correlated to the cumulatives at development year 0. And it's the same for every period. Okay, so for this data set, ratios don't have any predictive power. And if you continue with the study on our website, we introduce Murphy intercepts. We also introduce constant trends along the development periods done each accident year in the incrementals. Okay, so just remember that Mack is the default starting model in the ELRF, in the extended Lincoln family modeling framework of ECOFIS Plus, right? It is in ECOFIS Plus, it's in this module, and it's the starting model. It's the model that is estimated by default when you enter that module, and that's Mack. Okay, what about the Probabilistic Trend Family modeling framework? Well, what you try and do there is capture the trends in the 3 directions. And another integral part of the model, is the quality of the volatility around the trend structure. And the 3 trends are actually captured in terms of a graph. They're depicted graphically. So every model is represented by pictures. So everything is transparent. You know what assumptions the model has made about the data. You can test those assumptions. At the same time, when you do your forecasting, you don't have to use the most recent trends in your forecasting scenario going forward. You've got control on parameters, which is very important. This is a data set that I'm making up. Basically, it's got on the log scale, it's got a negative trend of 20%, 10% for these calendar years, 30%. This is also studied in a paper which is used by the CAS in its study program. I think it's subject 6. So these calendar year trends, in fact, project along the development years. This 30% kicks in for this accident year at that development year, but for this accident year at this development year. So I've simulated this data that we're quickly going to model M3AR5 And what we do at first is run the starting model, which only has one parameter in each direction. So the average development year trend is your minus 20 plus minus. That's the average level, and that's the average calendar year trend, 15.63, which kind of makes sense because if you have 10% for 4 years and or 5, I can't remember, 30% for between 2 years and 15% thereafter, it does make sense that the average is about 15.63%. What's a residual? It's the trend in the data minus the trend estimated by the method. Well, we know that in the early years you have a 10% trend, but the method removes a 15.63% trend. So in the early years, 10 minus 15.63 is negative. Between 82 and 83, 30 minus 15.63 is positive, and then 15 minus 15.63 is about 0. So we add a parameter there and add a parameter there, so we're now estimating a new model that has this structure. Those are the 3 calendar year trends. This is the development year trend, and that's the excellent year level, and this is an integral part of the model that represents the variance of the normal distribution, or you can find out the standard deviation. And we do have normal distributions. It's a part of the model. If you go back to the trend structure in the 3 directions, development year, calendar year, excellent year, but the calendar year trends, incidentally, the estimate of the 10% is only 8.73. The estimate of the 30 is far away from 30. Why is that? Well, you're only estimating a trend between 2 years, which have very few data points. And as a result of that, there's also a large uncertainty associated with that estimate. Whereas with the estimate of 15, because you had it for many years, there's very little uncertainty associated with it. The trends in the 3 directions actually look like this. And then you'll see that if you look at each excellent year going down, this is the first excellent year, 1978, there's a kick up of about minus 20 plus 39, it's about almost 20%. But each kick up as you go down the excellent years is 1 development year earlier. And that's also available in the PowerPoint display. So if you look at the resultant runoff for any excellent year, the kick up of the plus 10% here is always 1 year earlier, and that's an axiom. As you go down the excellent years, it always kicks up the 30% 1 year earlier, 1 development year earlier. Okay? All right. Now, if I were to conduct any forecast with this model, all my assumptions would be transparent. That's what I'm assuming about the decay. That's why I'm assuming going forward that I can change if I want to. I've got control on parameters. I'm assuming that the normal distribution has a standard deviation of close to 0.1, and that's the way I project normal distributions on a log scale, and then I bring them up to log normal distributions on a dollar scale. And all this is explained with lots of examples in these demonstration videos. One thing I do want to show you very quickly, and that is that the Mack method, in fact, does capture trends along the calendar years, especially if it's constant. If it's not constant, it can't do that, but you don't know how much. So what I'm going to do is that, and a lot of it is actually explained again in our demonstration videos on our website, that Mack does capture trends, but it doesn't have any descriptors of what it actually measured from the data. And in the residuals, you can only see the difference between the trend in the data and the trend estimated by the method, but you don't know what the trend estimated by the method is. So what I'm going to do is a very simple simulation for you. I'll go to SDF, and what I'm going to do is I'm going to simulate a triangle, and let's suppose we simulate it where the level is equal to 10. It's got an inflation, say, of 10%. The decay is minus 30%, and let's suppose the variance of the normal distribution is 0.08. So I'm going to save the model parameters as the true parameters. And this data will also be useful when we look at at some of the real data sets we'll study in terms of bootstrapping samples. So let's say let's call it true parameters. Oh, the capitals. True P. So it's Sim 9. If I go to models and go to Sim 9, I can run the true parameters, which are -30, 10, and level 10. I can estimate now the parameters from the data. So that's the estimate of the parameters, -29, around 10, and this should be around 10 also. Okay, and these are the residuals. Okay, and they look pretty straight. All right. If I now set the trend to 0 in my method, so now I've got a method that sets the trend to 0. This is a little bit of a study also on the residuals, not just the Mack method where we'll look at the moment. So the method has a trend of 0, but the data you can see has got a trend larger than 0 because we're looking at the data minus what is the trend estimated by the method, which is 0. So you can see that the trend in the data must be larger than 0. In fact, we know it's around 10%. If I do a forecast now, I'd get an answer that's way too small. And you can also see that I'm underfitting all these calendar years. If I now estimate the trend in the data, incidentally, this study is very important in terms of looking at the triangle groups ABC, triangle group LR high, and triangle group ERHOFO that we'll study also in terms of bootstrapping Mack and the optimal PTF model. If I now estimate the trend in the data, which is around 10%, and now forecast with that trend, I'll get a much larger answer. If I set the trend in the data to be 20%, I can do that. I've got control. Sorry, the trend in the method to be 20%. And estimate that, then the trend in the method is much larger than the trend in the data. You can see method data trend minus method trend is negative. In fact, because we know that in the data we have a 10% trend, and from it we're subtracting 22. That's what we set up in our method. We've got a negative trend of around 10%. If we do a forecast now, we're going to get an answer that's way too large. Okay? That's the only sensible answer, the one in the middle. So we showed you we can get an answer that's way too small because the trend in the method is much lower than the trend in the data. This one, the trend in the method is very close to the trend in the data, and that one, the trend in the method, is much larger than the trend in the data. Okay, if we now close PTF module and we go back to the triangle group and we cumulate Sim 9, so let's cumulate it. So just transform it. I guess I'll do it that way. Transform. So now we should have the cumulative version of it. If we now apply Mack to that and look at the residuals, you notice they're pretty straight, but I know there's a 10% trend in the data. But the Mack method doesn't tell me what the trend is. So the Mack method, as explained on our demonstration videos, the other demonstration videos, does capture some of the trends along the calendar years. Especially, it does a pretty good job. It might do a pretty good job when it's relatively constant. Okay? Doesn't mean it's got any predictive power. Okay? Doesn't mean it actually has any predictive power. It doesn't mean you don't need an intercept. But the residuals versus calendar year would look relatively flat, but you don't know what the trend, actually they're a little bit skewed also. You can see there's a bit of skewness here. You don't have normal distributions. We had normal distributions on a log scale, but we don't have them on a dollar scale. So the Mack method does capture some of the trends in the data, but you have no description of it. You don't know what. All you know is the difference. The difference is approximately 0. Whereas on the other side, where we're in PTF, the model gives you a description of the trends estimated in the data in terms of pictures, and if the residuals are evenly spread around 0 and you can test for stability and whatever, then you know that must be also the trend in the data. Thank you.